Hi, and welcome to part 3 of our u-substitution series for our Calc 1 videos. And in this video, we're going to specifically take a look at a few examples here and say, why are they a fraction? So I'm going to give you a bunch of rational functions, and from the beginning, we're going to have to take a step back and pause and determine, why is this a fraction? So let's look at these. And primarily we're going to be dealing with the indefinite integrals because we're really more concerned with, again, why is it a fraction, and then the evaluation of how do we figure out what that antiderivative would be. So we're not only going to antiderive these, but we're also going to answer the question, why is it a fraction, or what are we supposed to do with it? So in question 1, I can see that this is not necessarily a u-substitution problem. This is a separate and reduce. And so we have been calling it that. You might call it something different, but we're going to say separate and reduce. You can also look at this as x to the 1/2 and maybe bring it up to the numerator as x to the negative 1/2. So maybe you look at it not as a division problem, but maybe as a multiplication problem like so. Or you can look at it as the quantity x cubed over the x to the 1/2 minus 2x to the 1/2. And we can do some algebraic manipulation before we do our calculus. So I'll kind of highlight this right here because this sort of answers our question. All of my bases are x, which is another key indicator that I know I'll be able to combine these together nicely. So even before I integrate or figure out how I'm going to integrate, I want to do this algebraic manipulation. So I divide these, but again, if you distribute this in, it is the same thing. So I should get the quantity. Make sure you have parentheses there. And this will become 6/2 minus 1/2 is 5/2 minus 2x to the 1/2, 1 minus 1/2. And that's actually what we are integrating. And so this will become, I can just do power rule here, right? Add 1 to my exponent. And again, I'm going to leave a space. For those of you that haven't seen part 1 and 2, I'm going to leave a space here before my variable or base, because I know I have a fractional exponent. So when I add 1 to that fractional exponent, I'm adding 2/2, so I do get 7/2. But instead of dividing that x by 7/2, we multiply it by 2/7. And so I just left some space to write that coefficient in front of my base or variable. Minus 2 times, again, I'll leave a space. I have a fractional exponent. So if I add 1 to do power rule, that becomes 3/2. Oops, that went funny. And then instead of dividing by 3/2, I'm going to multiply by 2/3. Don't forget your plus c, which is our constant of integration. You can certainly leave it like this if you wanted to. I could also just multiply that in and say that that's 2/7 x to the 7/2 minus 4/3 if I didn't really want to type, the 2 times 2 if you're typing it into a system or anything like that. Okay, so I left question 1 on the screen, but let's take a look at question 2 over there to the right, and let's pause before we just jump to determining, what that antiderivative is. Maybe let's see if there's some algebraic manipulations or some rewrites or something that we want to do so that we can answer the question, why is that one a fraction? So first thing I might say or suggest is that 6 is a coefficient. So maybe in order to see why is this a fraction, maybe that 6 could be written out in front of my integral just like we could do with the limits. It's sort of the same idea there. All right, so now I look at this. This is not a separate and reduce like question 1, because although I am dividing technically by one term, it's a square root function, I only have one term in my numerator, so there's really nothing for me to separate and reduce, so this has to be something else. Well, and it's not going to be u-substitution either. I can show you why on the next question. So we should actually recognize this derivative, meaning we should recognize the trig function, or really inverse trig function, that gives me 1 over the square root of 1 minus x squared as its derivative. So this one is inverse trig. That is the reason why this one is a fraction. So I know that if I differentiate inverse sine of x, I get what I just circled there in pink. So this is really just 6 inverse sine of x. Okay. But that is contrasted with number 3. Now I'm going to write number 2 next to it just so you could see the difference in problem. So there's what we started with for number 2, and here's what we're working with number 3. And why are we saying that number 3 is u-substitution and not just inverse trig? Well, remember, we moved that 6 out in front, so we had a constant, right? Even though 6 is a constant, sometimes it just gets in our way. So we have a constant in the numerator, not a variable. So that was the inverse trig that we said for number 2. But number 3, when I look at it, has a variable in my numerator. So that's going to allow me to try u-substitution and see if that's going to work. So if I let the 1 minus x squared be my u, my du is negative 2x dx. And again, if it doesn't match exactly with what I have here in that numerator for a constant, go ahead and pull that coefficient out front. It's just your constant coefficient. So that can come out front. I need a negative 2 inside. So I'm going to divide, so I'm going to multiply the negative 2 inside. So I'm going to divide the negative 2 outside. So I end up with negative 2 times the antiderivative du over u to the half. So this worked out perfectly for u-substitution. And then I integrated it, and I was done. Again, the difference being just one little variable. So if you don't step back and pause and really look at what you have, you're going to think more than not that it's u-substitution or it's inverse trig. You really have to identify that difference. All right, so let's try something else with number 4. Now, I might look at this and say 1 plus x squared in the denominator. Oh, that does look like inverse trig, but I also have a variable up here in the numerator, so let's try u-substitution. And I don't think there's anything wrong with you trying u-substitution first. So if I do that, I'm going to let my denominator be my u, and my du then will be 2x dx. Again, this is assuming that you've completed part 1 and 2 videos for u-substitution. This is sort of wrapping it up, or hopefully is tying it all together for you. All right, well, the problem with this du is that it is one term. And if you look at your numerator over here, all of that would have to be du because all of this is my u. So all the rest of it would have to be comprised by du. And the problem is you have 2 terms in your problem, but you have 1 term in your du. So there are more terms in your problem than what you actually found in your du. So it can't only be u-substitution. Well, it's kind of similar to number 1 then. I need to separate this out. So we're going to write separate into 2 fractions. Sometimes you might need 3, sometimes you might need 2. Most commonly it's probably 2. So from the beginning, this would be equivalent to 1 over 1 plus x squared, don't forget your dx, plus x over 1 plus x squared dx. Now think back to common denominators. I can add, like so. So if I have the common denominators, I would just say that that is my common denominator, right? And I would just add across the numerators. So what I've written is equivalent to what I've started with. I've just separated it into two different integrals because my integration techniques are not going to be the same. This right here is the u-substitution. But this first one is not u-substitution. We talked about why. There's no variable in that numerator. So if I identify 1 plus x squared to be u, I need a variable of x somewhere evident for my du, and I don't have that. So this should scream inverse trig to you. So I'm going to say first separate it into two fractions, then you have u-substitution and inverse trig in the same problem. So this first one is actually the antiderivative of 1 over 1 plus x squared is inverse tangent of x plus, and I'm just going to write this out because I already have the u-substitution stuff written down over there to the left. So I will throw a 2 in, so that way I have my du, which means I need to put a 1/2 out front. So then I have inverse tangent of x plus 1/2, and then that becomes du over u. And we should have seen this a fair amount of times now, that becomes 1/2 natural log absolute value of u. Don't forget your plus c. And my u is 1 plus x squared. So I'll put that back in. Now there are a couple of things that sometimes people do. This would be a great answer, and certainly you can finish with that. The absolute value bars here are a little bit redundant because no matter what you're putting in for x, you're squaring it. So even if you put in a 0 for x, you're squaring it, and then you're adding 1. The lowest that that's going to be is ever 1. If you put in a negative, again, you're squaring it, it turns positive. So I don't really have to worry about it. And also some people like to use natural log properties, so that is actually the exponent of that argument, so they'll just do that instead. My only caution to you is you can't take the square root of individual terms, so some people like to continue algebra and there's nothing else you can do there. All right, so keeping that in mind, one last one that we're going to look at. Now, it might come to your thoughts to separate this, right? Because I can kind of see the resemblance from the previous problem. I'm dividing by x squared plus 1, which looks maybe like an inverse tangent antiderivative. And I can see the 1, I can see the u sub, but then I have other things going on with that x cubed and x squared. Well, let me just give you a numeric example of what this would be like. This would be like me writing 10/7. And you would tell me that this has a whole part of 1, right? Because 7 can go into 10 one time. And then there would be 3 left over, so 3 over 7. So this would be the same thing as 1 and 3/7. This being my whole part, and this being the fraction part, or what you're used to seeing as the remainder. Well, if you think about integration, if something turns whole or turns polynomial, I can integrate it all day long using power rule. I am concerned right now about why things are fractions. So when we say that, we're really talking about fractions that are less than 1. So if the power in the numerator is greater than that power in the denominator, I have something like 10/7. So what we're required to do first is to actually perform long division. Those of you that ever wondered, when am I ever going to use long division? Here's another example. Besides slant asymptotes that we talked about last chapter, here's another example. I'm just making sure I'm copying it down correctly. So I'm going to divide x squared plus 1 into that x cubed plus x squared minus x minus 1 to figure out what is that whole part, which I know I can integrate, and then what is that fractional part, which then I'll figure out how I have to integrate. All right, so let's start this long division process here. X cubed is my first term, divided by x squared, which is my first term. So that's an x. I'll distribute that. So I get x cubed plus x. Help yourself out. I'm going to write my like terms underneath each other so that when I subtract the whole row, right, or change your signs, I can add straight down. So x cubed minus x cubed adds to 0, and I'll carry down x squared minus 2x minus 1. And as long as you can keep going, keep going. Well, can I take x squared and divide it by my leading term, which I'm dividing by x squared? Sure, I get plus 1. I'll distribute that. So I get plus x squared plus 1. And then again, go through and change your signs because you subtract the whole row. X squared minus x squared should add to 0. So then I get negative 2x minus 2. And if you try to divide now, I would take negative 2x divided by x squared, and I would see that that leaves me with my remainder. So this problem is really equivalent to, I'm going to write what it should be equivalent to, antiderivative of the whole part, which is x plus 1, and I'll do that separate here, plus the fraction part, negative 2x minus 2, and again, that's over what you were dividing by, x squared plus 1. Don't forget your dx's, please. All right, so I can integrate x plus 1. That's like that whole part, right, that we saw when we did 10/7. So I can integrate that using power rule. That's x squared over 2 plus x. And then I'm going to factor out a negative 2 from that numerator so you can see something else. I did something that hopefully will help us here. And now if I look back at number 4, if I can get them both on your screen without being too small here, my number 4 that I did, 1 plus x over 1 plus x squared, is the same question as here. So I'm going to try to keep that answer on the screen because that answer is going to get shifted over here as well. So this is x squared over 2 plus x. The only difference is I'm going to have a negative 2 coefficient in front of that whole thing. So whether you distribute the negative 2 throughout or leave it in front is up to you. So for now, I'll just leave it in front. And I'm just going to do the first one that I boxed. Inverse tangent x plus 1/2 natural log 1 plus x squared in parentheses or absolute value bars plus c. You can certainly distribute that negative 2 if you would like. So my reason for why is number 5 a fraction, right, because we've been writing down a reason, I had to do long division first, and then I had a whole part or a polynomial, power rule for integration, and the fraction part was like number 4. Okay, so that was a long division first. Sometimes you can use synthetic division if you're lucky enough to divide by a linear factor there, but that's okay. So I hope you found this video helpful because once you get working with u-substitution, sometimes we think every fractional or rational integration function that we see has to be u-substitution, and that's not necessarily true. So just trying to open your eyes at the different variations that you'll see, and I hope you found that helpful. Thanks for watching.